Okay, so am I audible? Hello? Can you hear me? Okay, yeah, thanks. Some internet connection issue. Not able to provide lecture from my home, so I had to rush to the institute. So that's why delay. Also, I don't have a my system. So let me download it. Not in a minute or two. Okay, so my screen is visible, right? Okay. So what we are going to do today is um, trajectory planning, okay, or trajectory generation. Say I have, say I want to take an object, okay, from one position to another position, okay. So say I know using forward kinematics that if my joint variables are this and this, then I know what is my end effector, right? Similarly, using inverse kinematics, I know if this is my end effector's position and orientation, then I can calculate what should be the joint variable values, right? So that's using inverse kinematics. Now, say I want to pick an object in a particular orientation, then I know what should be the end effector position and orientation. Then say I pick that object and I have to take that object and put it somewhere else, okay, somewhere else in some other orientation, which means there will be another position and orientation. Okay, and even for that new position and orientation, we do know what should be the joint variable values, right? So I know joint variable values for the initial position as well as for the final position, right? Okay, I have problem with my voice. Let me try. Okay, how about now? Am I audible? Okay, okay. So, but in between, okay, in between how the end effector position is going to change or how the joint variables are going to vary. Okay, so what exactly thing I need to solve is, say I know at a particular instant of time what should be the joint variable values. Okay, and after some time I know what should be the joint variable values. Okay, but in between the joint variable values are going to change with respect to time. Okay, and what kind of function is going to be there. Okay, by choosing those functions we are planning the trajectory of the end effector or trajectory of the whole manipulator. Okay, so how are we going to do? But before that, while we choose, we need to consider certain things like as we discussed in the inverse kinematics, it can have multiple solutions. Okay, and we need to choose one of the solution, and accordingly we need to choose our trajectory planning. Okay, so that's one thing we need to consider. And the first thing what we are going to do is we are going to use cubic polynomial, and using cubic polynomial we are going to construct the trajectory path. Okay, so how the problem has been defined? The problem is defined in the following manner. Say these are the joint variables. Say this is one of the joint variables. So for a 6 degree of freedom system, we will have 6 theta values. Okay, let's say among those 6, this theta is one of that degree of freedom. Okay, and when time t is equal to 0, we have theta which is equal to theta naught. Okay, and when theta is when t is equal to the final time, let's denote that by tf, then at that time the theta should be theta f. Okay, but in between what should be the theta value? So what we are going to do is we are going to assume the theta is going to vary from here to here in the form of a cubic polynomial. Okay, so we are going to construct an interpolation using cubic polynomial. And how are we going to construct? So basically, so this is my t-axis, time axis, this is my theta, and initially it has to be here, and after some time tf, it has to be here. But I can reach from here to here within this time through any path, right? So I could go like this, or I could go like this, I could go like this. But among those, I'm going to choose a cubic polynomial. Okay, so if I choose a cubic polynomial, I will get, I'll have the form in this manner. Okay, so this is the cubic polynomial. So with respect to time, it's going to vary in this form. Okay, so I have to choose my a0, a1, a2, and a3 such that my theta is equal to theta naught when t is equal to 0, and theta is theta f when t is equal to tf. Okay, but here if you see, we have two constraints, but we have four unknowns. Okay, so now we need two more constraints so that I could calculate all the four coefficients. So can anyone say from where I will get two more constraints? So we have four coefficients, a0, a1, a2 and a3. Okay, and in order to calculate all these four, we need four constraints or four equations, but what we have is two equations. So the initial theta has to be theta naught and the final theta has to be theta f. So what are the other two constraints? Anyone?
Velocity or acceleration?
Okay,
you know the
so
value.
okay, so maybe we have to have the constraints from its derivative. Okay, okay. So now in the pick and place, okay, I know the initial position and final position. What about the initial velocity and final velocity? So what will be the initial velocity and final velocity? Say when I pick and place at a particular point. So what will be the initial and final velocity? Can anyone say? That instant of time, what will be the velocity while you are picking? Say whether your robot is picking or whether you are picking. While picking, what's the velocity? Yeah, okay. Visible? Yes, right now I'm not showing the PDF. Okay, so actually the velocity will be 0. Okay, the initial velocity will be 0 because while picking you will not pick while the end effector is moving, right? So while picking, the end effector will be at rest position, and while placing at some other position, even at that time the end effector velocity will be 0. So the constraint is the initial and the final velocities are 0. Okay, so in a mathematical sense we can write those equations or those constraints in this form. So theta dot is equal to 0 and at t is equal to 0, and theta dot is equal to 0 at tf is equal to 0. Okay, now we have four constraints, and now we can calculate the four coefficients. Okay, so this is the position as a function of time, and if I take a time derivative, I'll get velocity as a function of time and acceleration as a function of time. Now let's impose those four constraints, okay, or four conditions, and let's try to calculate what is a0, a1, a2 and a3. Okay, so this is the condition. So when t is equal to 0, if you see from here, when t is equal to 0, theta is equal to theta naught. Okay, from that what we can say, in this equation we can put t is equal to 0. If I put t is equal to 0, theta naught is equal to a naught. Okay, so that's one equation when we impose the first condition, and similarly if we impose the second condition, when t is equal to tf, I'll get theta is equal to theta f. Okay, and then velocity has to be 0 at t is equal to 0 and t is equal to tf. So from that I'll get theta is equal to a1 is equal to 0 and this whole thing is equal to 0. So now we have 4 equations and we have 4 unknowns, and if we solve for this, what we will get is a0 is equal to theta naught, a1 is equal to 0, and a2 and a3 are given by this equation. Okay, so that's how we construct the trajectory if we use cubic polynomial. Okay, so before I go further, I would like to ask, do you have any questions? Okay, so if there are none, then we'll go for this example. So it's a single link robot. Okay, so it has only one arm. Okay, and it's a rotary joint. Okay, and if you see, theta is equal to 15 degree. Okay, it is a theta is equal to 15 degree, and it is desired to move to a position such that the final position will have a theta value 75 degree. Okay, and this change in position has to happen within 3 seconds. Okay, now what we have to do is how theta is going to vary as a function of time. Okay, for that we need to use a cubic polynomial. Okay, we need to use the cubic polynomial, and we need to calculate all the coefficients. And then in this picture, in this problem, they have asked us to plot the position, which means theta, velocity, theta dot, and acceleration, theta double dot, how they are varying as a function of time. Okay, so now can someone say from this question, okay, because in this question we have to know what is theta naught, theta f, and tf. Okay, if we know these things, then using these 4 equations I can calculate what is a naught, a1, a2, and a3, right? So from this question, can someone say what is theta naught? What is theta naught? So from this problem, can someone say what is theta naught?
15 degrees.
Sorry. Yeah, that was 15 degree. And similarly, can someone say what is theta? Someone else say what
75.
is theta?
75. It is 75. Theta f.
Okay, thank you, thank you. And then TF is 3 second, right? TF is 3 second, and then we could use these formulas and we can calculate all the coefficients. Okay, and if we do that, and if we plot, it's given in this figure. Okay, so this is how the change in theta will look like, and this is how the change in velocity will look like, and this is how the change in acceleration. So if you see, the acceleration is linearly varying and velocity is quadratic, and this is cubic. Okay, fine. Now what we're going to do is say, for example, maybe I will go to that respective page and I will show you the problem. Right, okay, so if you see, in this problem, say you want to go from this position to this position, but you can't choose any path. Okay, because there is a possibility that there will be some constraint. Okay, so at that time maybe you have to go, instead of going like this, you may have to go from here first to there, and then maybe after that you will be going from this point to this point, and then you will be reaching here. Okay, so accordingly theta value will also we can't decide that theta, the trajectory path, just using theta naught and theta f, and also with tf. Okay, so we have to decide with some intermediate points. Okay, so those intermediate points, yeah, those intermediate points, okay, are known as via points. Okay, so now what we are going to do is we are going to construct cubic polynomials. Okay, now how are we going to construct the cubic polynomial? We are going to make a segment of the total path, okay, into, say, so n cubic polynomials. Okay, and each segment will have 4 coefficients, and we have to identify all those 4 coefficients. Okay, or in other words, if you see this picture, probably you will have an understanding. For example, this is t and this is theta. Maybe due to some constraint or due to some reason, okay, uh, between some t equal to t naught to ta, we need to vary the theta like this. Okay, and then from ta to tb, we need to vary the theta like this. Okay, then in this interval I have to vary like this, and in this interval I have to vary like this. Okay, even though I finally I need to vary reach theta naught to theta d. Okay, I can't do it like a cubic polynomial from theta naught to theta f, but I have to go through these points. Okay, the reason we have to go through these points is because, I mean, one reason could be because there will be some constraint, another reason could be something else, depends on the application. Okay, so these points theta a, theta b, and theta c are known as via points. Okay, so because it has to go via this point. Okay, so now what I have to do is I have to come up with a cubic polynomial between this point and this point. Okay, and between this point and this point there will be another cubic polynomial. Okay, and then there will be another cubic polynomial, there will be another cubic polynomial. So totally, for this configuration or for this trajectory planning, I have to construct 4 cubic polynomials. Okay, if I have to construct 4 cubic polynomials, can anyone say how many coefficients I have to identify?
16 polynomial.
Yes, thank you. And maybe you could also type it. Okay, thank you, sir. So in total we require 16 cubic polynomial, sorry, 16 coefficients. Okay, now how are we going to construct those cubic polynomials? Okay, so initially at this point we know the initial position, which is theta naught, and the initial velocity is theta dot, which is 0. Okay, the initial velocity, which is 0, and the final position is theta d, and the final velocity is theta f. Sorry, final velocity is 0. Sorry. Okay, now can I come up with some constraint maybe at the via points? Okay, so can someone say any condition, let's say at this particular point, the point at which t is equal to ta? When t is equal to ta, using ta to tf, we will go to this. So see, at this point, I know the position and the velocity. Okay, so those are 2 constraints or 2 conditions which I have to satisfy. Here I have 2 conditions which I have to satisfy, which is the velocity has to be 0 and theta has to be theta d. Okay. What about the condition which I can have over here? Each TA, TB, and TC. Okay. And at those points, what do I know? So one thing I know is theta. Okay. Because when t is equal to ta, theta has to be theta a, right? So I know one condition at this point, similarly one more condition at this point, and one more condition at this point. Okay. So I know two conditions at the beginning and end. Then I have one conditions in the middle. Okay. So far I have 2 plus 2, 4, 5, 6, 7. 7 conditions. Okay. What else can I say about the constraints? What other constraints I can have? What other constraints I can have? Anyone? Yeah, maybe you can unmute and speak. What other constraints we can have, particularly at wire points? The remaining constraints are going to be at wire points.
You know the velocity or acceleration, we can use it, sir.
If we know the velocity and acceleration, yes, we can use it. But do I know the velocity and acceleration? Because, okay, tell me one thing, whether the velocity at this point will be 0. Because I know that while I'm picking, the velocity has to be 0, and placing, the velocity has to be 0. But at wire points, whether the velocity has to be 0? Can anyone answer? At the wire points, at this point, this point, this point, whether the velocity has to be 0? Okay, so why don't we make a poll? So how many of you are saying the velocity has to be 0? If you think the velocity has to be 0 at wire points, say yes. Okay. So at this point, whether the velocity has to be 0. These are just wire points. Okay. Maybe 5 more seconds. Okay, okay. Okay, so let's publish the result. So most of you have said that velocity has to be 0 at this point. Okay, so I'll tell you how does it look when the velocity is 0 at that point. Okay, I'm able to switch on the Yes. Okay. So if you see, say this is an object, okay, and say assume that this is an end effector, and you're going to pick. While you are picking, you will not while moving and pick, right? So the end effector has to um, be at rest position, and then it has to pick. Okay, so therefore the initial at t is equal to 0, it has to have a 0 velocity. Okay, and at the same time, say this is the position where it's going to place. Okay, while it's placing, okay, it should not throw and move, right? It should put it in rest, and then it has to move, right? But say while taking this object from here to here, but while moving, I'm going to move via this point. Okay, say instead of moving like this, I'm going to move like this. But while moving like this, because say there is some constraint over here. Okay, while moving like this, do I have to uh, make this one make the velocity 0 and then reach over here? So all I have to do is I have to go through this path, but is it necessary that I have to stop here and then move to this point? Maybe can anyone answer now? Is it necessary to stop here? Because this is the picking point and this is the placing point, but this is the via point. Okay, so do I have to stop and then move? Can anyone answer? Not necessary, right? It's not necessary. And one more thing, if I do that, what will happen is this kind of jerk will happen. Okay, and just stopping and then starting. Okay, so that's the problem. Okay, so and because of that, okay, um, it's not necessary. Okay, it's not necessary that the velocity has to be 0. Okay, but the constraint which we are going to add is it has to be smooth. Okay, because the velocity should not change abruptly. Okay, the velocity should not change abruptly. Okay, so that will provide me one more condition. Okay, that will provide me one more condition at this point, and this point. Okay, another condition is the theta value has to be smooth. Okay, which means uh, even for a cubic polynomial for this segment and the cubic polynomial for this segment, okay, this theta value has to be same at t is equal to ta. Okay, so there should be a continuity at ta for theta. Okay, and there should be a continuity at ta for theta dot as well. Okay, so that will add up additional constraint, and with that additional constraints, we can construct cubic polynomial for each segment. Okay, for each segment, and I believe those constraints are given over here. Is it given? Let me check. Okay. Fine. So let's see this problem. Okay. So example 7.2, and here we need to solve for the coefficients of two cubic polynomials. Okay, which means there is only one via point, and so let's read this problem first. So we need to solve for the coefficients of two cubic polynomials. Okay, that are connected in a two-segment spline with continuous acceleration. So here the acceleration should also be continuous. which means at that instant of time, theta double dot of the first segment as well as the second segment are same. Okay, at the intermediate via points, the initial angle is theta naught, and the via point is theta f, the intermediate point, and the goal point, the final point is called as goal point, is theta g. Okay, so now the first cube is this one, the second cube is this one. Okay, now we have, since we have two cubic polynomials, we have total 8 coefficients. Okay, so let's see all the conditions. So here the notation is as follows. The first one represents the first, which cubic polynomial I am representing. So since this is the first cubic polynomial, so the first number is 1. Okay, and here the number is 2. Okay, and this is which coefficient I am talking about. Okay, so whether it's a t to the power of 0 or t to the power of 1 or 2, that's the representation of the coefficients, and we need to calculate all these coefficients. Okay, what are the conditions? When theta is equal to theta naught, yeah, then this equation has to go to 0 when t is equal to 0. Okay, and similarly, yeah, this is the intermediate when tf1. Okay, here by tf1 they mean the time at the uh, end of the end of first cubic polynomial. Okay, so that's what tf1 represents, and here they represent as a tf2, which means that the end time of the second cubic polynomial. Okay, so these are some constraints. Okay, theta naught from theta naught and from theta v, and then from theta g. So 3 constraints. Okay, and then similarly for second cubic polynomial, we have some more constraints. Okay, so in total, and also as I mentioned that not just position and velocity, but also the acceleration should be continuous. Okay, so with that we will get 8 equations, and if we solve all those 8 equations, we will obtain all the coefficient, and this is the list of the coefficients for which they have calculated. Okay, so once we derive such a equation, then in our coding, all we have to do is we have to substitute for theta v, theta g, and tf, everything, so that we will obtain the coefficient values. Okay, so now the question is it necessary that it has to be a cubic polynomial? The answer is no. We can also have higher order polynomials, and if we use a higher order polynomials, then if we have more constraints, okay, then we can take care of those constraints using this higher order polynomial, and it's more smooth compared to the cubic polynomial. Okay, but at the same time, the drawback is it's a bit difficult to calculate the coefficient, and it's the n segment of cubic polynomial, calculating the coefficients is some standard procedure. Okay, so yeah, that's one part of numerical methods course, and if we have to do some interpolation, and if we are doing the interpolation using cubic polynomial, then how to calculate the coefficient. Okay, so the calculation of coefficient, while we try to calculate the coefficient, we will end up with the tridiagonal matrix. Okay, and we know how to solve using a linear system if that system is having a tridiagonal matrix. Okay, there are many algorithms available for that. Okay, so before I go to the next type, is there any question? Any question with cubic polynomial and how to calculate the coefficients? Okay. Okay, then we'll go on to the other one. So it's not necessary that we always have to use cubic polynomial. So the other method is a linear function with parabolic blends. Okay. So what's a linear function? Say, for example, I'm moving from theta naught to theta f in this interval of time. So if I connect these 2 points via a linear function at that, so that's what the linear function path represents. Okay. But the problem with these thing is actually, I mean, it's a constant velocity. Okay, it's a constant velocity. If we take a time derivative of this one, then the velocity has to be constant. And what about the acceleration? The acceleration will be 0. Okay, so if we take a double derivative, the acceleration will be 0. If that's the case, we can't use this function alone for pick and place. Why? Because initially the velocity has to be 0. Okay, but in between the velocity has to change, and then finally once again the velocity has to be 0. Okay, just with this linear function we cannot achieve that. Okay, so for that reason we can't use linear function. But the advantage of linear function is in between it will move in a constant velocity. Okay, but how can I achieve that advantage but with the linear function? Okay, so for that what we will do is, for some region, okay, we'll use linear function, but in certain region, say at the beginning and at the end, we will use a parabola. So if you see, instead of a linear function, okay, instead of a linear function, what we will do is we'll include a parabola which is from here to here, and similarly a parabola from here to here. Okay, but in between it's a linear function. So now for this function there will be some coefficients and we need to identify those coefficients. Okay, let's see how to identify those coefficients. Okay, once again we'll see what are the constraints available. Okay, do I have to see the constraints available? Yeah, let's first see what are the constraints available. So what about the constraint, or what about the condition at this point? One is, at this point theta should be equal to theta naught. Okay, so what about the velocity at this point? Can anyone say what about the velocity at this point? Okay, it's a question whether trajectory planning can be studied along with frames. I'm not sure. I couldn't get the question correctly. Here, what we are doing is we identify using our variables. Okay, how they are going to vary, because the joint variable is the one which we are going to control. Okay, using our motor or using our actuator. Okay, while giving the input signal to the actuator, how, I mean, it's fine what should be the initial position and final position, but how in between the things are going to change. Okay, so that we have to decide, right? And in order to decide, yes, and the velocity at that point is 0. Okay, and velocity at this point is also 0. Okay, and at this point we have a constraint that t is equal to tb. Okay, um, the theta has to be continuous. Okay, the theta has to be continuous, and also the velocity has to be continuous. Okay, the velocity has to be continuous. Similarly, here the theta has to be continuous and the velocity has to be continuous. So those are the constraints. So here one constraint is theta has to be 0. Sorry, theta has to be theta naught and velocity is 0. So two constraints, and theta is equal to theta f, and theta dot is equal to 0 at this point. So two more constraints, and here the position has to be continuous and the velocity has to be continuous, and the same over here. So in total we have 4 constraints, sorry, 8 constraints. Okay, now how many coefficients are there? So for this one, the coefficients are, okay, can someone say how many coefficients are there for a parabolic function? For a cubic function, we had 4 coefficients. For a parabolic function, how many coefficients are there? No. Okay, what about for a linear function, how many coefficients are there? Can someone say? For a linear function, yes, there are 2 coefficients. Then for a parabolic function or a quadratic function, so parabolic function is nothing but a quadratic function. Exactly. So it has 3 coefficients, which means for this segment we have 3 unknowns. Okay. Similarly, for this segment we will have 3 more unknowns, and for this linear segment we will have 2 unknowns. So in total we have 8 unknowns. Okay, and we have 8 constraints, right? So at each point we have um, 2 constraints. Okay, so total 8 constraints we have to calculate 8 coefficients. Okay, but there's one problem. The problem is we do not know what is TB. Okay, so we can choose this TB anywhere. Okay, we can choose this TB anywhere. Accordingly, for example, if let's say, yes, if you see, if we choose TB at this point, okay, finally I will end up this point when t is equal to tf. If I choose TB at this point, even then I'll choose, I will end up at theta f when t is equal to tf. Okay, on what basis I have to choose my theta b? Yes, on what basis I have to choose my theta b? So can anyone give a guess? Can anyone say how can I choose my TB? This time. Okay, it's not necessary that has to be right, but you can give some answer. Okay. Okay, so maybe I'll give one more hint. Okay, for this case, okay, so it has one TB and it has another TB. Okay, so when for one case TB is small, another case TB is large. Okay, for which case the acceleration, okay, the acceleration at any point will be more. Can someone say whether for the case TB is equal to small or TB? Maybe I'll give a poll. Okay, so when TB is equal to, okay, I'm going to make a statement and you're going to say whether that statement is right or wrong. Okay, when I'm saying when TB is equal to small, I have to apply more acceleration. Okay, or the theta is going to change with high acceleration. Okay, when TB is equal to small, that's the statement. Okay, if you're going to agree with that, say yes. Okay, so the question is the statement is when TB is equal to small, okay, then the acceleration is more. So that's the statement. If you agree, then say yes. Okay, maybe if you look at this picture, you will get some idea, I believe. In order to reduce my acceleration, should I choose this path or this path? If I choose this path, then TB is more. If you choose this point, then say yes. If you choose this point, then say no. Okay. Um, Fine, let me publish the results. Many of you have said yes. Um, Actually, the acceleration is more, sorry, the acceleration is less. Okay, when the acceleration is less when I choose this, sorry, this point, okay, compared to this point. So most of you have answered it correctly. Okay, and if I have to choose the very minimum and acceleration, then what I have to do is I have to choose this point as TB. Okay, but I can't choose TB beyond this point, the half point. Okay, but at the same time, okay, but at the same time, I'll be using very less linear segment path. Okay, so therefore, how do I decide what should be my TB? It depends on what is the maximum acceleration my actuator can provide. Okay, what is the maximum torque or force my actuator can provide? Accordingly, I can decide what should be my TB value. Okay, so if my actuator is more powerful, then I can choose my TB very small. If not, I have to choose my TB very large. Okay, uh, is that point clear? So Do we all know how to construct the um, linear function with parabolic blending? Okay, I'll take that as an S. Okay, and actually this is the little derivation to show that in order to minimize the acceleration, what should be my TB, and we'll end up with the TB is equal to TH. Okay. In this picture, it's shown that how the position, velocity, and acceleration will look like in the in different segments, okay, and different polynomial scheme. So, and then this is the last point, and with this point we can wind up this little chapter. So if you see, this is the initial point, or say this is the initial point, okay, this is the initial point, and this is one wire point, okay, these are the wire points, okay. Along with wire points, how are we going to construct a parabolic linear path with parabolic blending? Okay, so while constructing, what we will do is first we will make a line like this, okay, we'll make a line like this, and then what we will do is we will choose some points over here, okay, we'll choose some points, and these are the points between which the trajectory is linear in shape, okay. In between they are parabolic, okay, in between they are parabolic. From here to here it's parabolic, from here to here it's parabolic, from here to here again it's parabolic, but in between it's linear, okay. Here it's linear, here it's linear, after here it will be linear, okay. I think it's a rest position, therefore the change is null, okay. But here in the linear segment with parabolic blending, it will not go through that via point, okay. So that's very important. In cubic polynomial it will go through that via point, but in the in this one, the parabolic blending, it will not go via that point, but it will go near to that point, okay. So that's one thing we need to have in mind. And similarly, like in cubic polynomial, we have to come up with the constraints at each via points and at the end and goal point, and then we need to calculate the coefficients of all the segments, okay. So yeah, that's what the trajectory planning is about, and I leave these things as a go through yourself, okay. Here there are various schemes, but they are a little advanced one. So yeah, mainly those are the things which I wanted to discuss in this session. Any questions? Mainly you is like now you know if you know what should be the end effector position initially and finally, or and also intermediate, then you will know what should be the joint variable values at the initial configuration, final configuration, as well as for intermediate configurations, okay. So that will provide you what should be my theta naught, theta f, and theta v, theta v1, theta v2, and everything. Okay, and then once you know all these things, then you will be using this cubic polynomial or a linear polynomial with parabolic blending, and you can construct the trajectory. You can construct the trajectory. Right. So, any questions? Okay. So, if there aren't any questions, then I would like to ask. Okay, can you please give an idea how this trajectory will implemented on MATLAB or Simulink software? Okay. See. Okay. Can you unmute and can you elaborate your question, because I don't understand what do we mean by implementing, because finally if we find the equation and if we give the coefficient, then that will provide me what is my theta at each time step, right? And that's just a simple calculation, and not a very difficult thing in implementing in MATLAB or any other software for that fact. Maybe if you could elaborate that question, then I will have some understanding. Okay, so meanwhile, construct his question. Okay, maybe by today I will open that. What is it? The Google form. I will share that Google form regarding that question paper. Okay, so where you can answer that question paper, and yeah, so that's one thing I wanted to ask, and so I also wanted to know how is the question paper and how is the sessions going so far. So maybe a little feedback at this moment I would like to get. So can anyone? Dynamic part is difficult. Yeah, it is difficult, and that's one of. I mean, it should. I mean, we need to take much time, and we need to spend on that, but we weren't able to do it. Yeah, I mean that's one of the reason I omitted many questions from that for the evaluation. Okay, the question is very difficult. For that reason, what I'm going to do is tomorrow in the last session, what we are going to do is I will discuss the question paper. Okay, so maybe after we have a discussion on the question paper, then you can give an attempt. Okay, so it's not that I'm going to provide the answer, but I'll try to give some hint. Okay. Okay, thank you. And okay, so please give us time to submit the answer paper. Yes. So the thing is, I'll discuss it in the last session. So probably maybe by tomorrow night, 8 o'clock. Okay, so by 8 o'clock you may have to submit it. Okay. Computations, it's not necessary. Okay, you don't have to use computations, because while I was taking those questions, I have just used a calculator. Okay, so while identifying the answers, so it's not necessary that you have to use a computer or you have to use MATLAB to solve. Okay, I mean, if you use and if you learn, that would be nice, but it's not necessary. Okay, and then if you just I mean, most of the questions I have taken from that book, the book by John J. Craig. Okay, so if you just go through that book and also if you just go through the lecture, then it will be possible. Okay, yeah, because we can't delay further, because I also have to submit things at Atal portal. Okay, so yeah, so that's the idea, and by today evening I will um, send the link so that you could submit the Google form, okay, for the answers. Okay, and while submitting, it will request your email ID and phone number. So for that you have to give um, your email ID and phone number which you have given at Atal portal. Okay, so that's one thing I wanted to convey. Yeah, right. So I think that's all, and maybe if you have any questions related to this or anything we have discussed so far. I think most of the questions will be from whatever we have discussed so far. Okay. Yeah. So okay. So if there aren't any questions, then we are going to have our next session, which is at 2:30. Okay. And that session is by Professor J. Krishnaya from IIITM Karnool, and he will be delivering the talk on artificial neural networks in robotics. Okay, so see you in the next session. Thank you all.